Okay, so there were a lot of different ways to write derivative, and it's important that we are able to recognize the different types of notation. So for instance, we had this one, which we would read as dy dx. Another way to say derivative might be this one, where we have y prime. Another way to say it might be f prime of x. And not as common, but also still there, is sometimes we have d dx of a function, okay? But all of these say derivative, and all of it says find the slope at a specific point, okay? So that's why we left so much space for that concept of what a derivative is. I would encourage you to maybe go back and try and draw some different pictures and see if you can describe the slope at different points. I think that's definitely an important exercise to think about. All right, then we kind of got into the computation part, okay? So we started to say, hey, in 3.1, we learned about that formal definition, and it was a lot of plugging things in and simplifying. And, you know, I wonder if this is so important, is there a shortcut? And that's where we started to look at some of these rules. So we spent some time looking at the power rule, okay? And we said even that there's something we really have to be careful about with the power rule, that the base should be a variable and the power must be a number. And that's really important because even though we haven't learned it yet, and we won't learn it for a few weeks, we're going to be looking at exponential functions in a bit, and those are going to have their own set of rules, okay? So we practiced a few examples here where we looked at just like one term at a time and how to use that product or that power rule. And we also looked a lot at why Judy would assign something that seems like isn't calculus, like what is 1/2 minus 1? Or how do I write x to the negative 5/3 as a radical, right? And the reason why was because it just gives us a little bit more access to plugging in numbers, being able to go back and forth between multiple forms. We talked a little bit about some special cases. All right, we talked a little bit about some special cases, the constant rule, the linear rule, and folks were also able to identify why those are true through pictures. And I think that's an important part of the conversation I want to encourage you to have with each other is if the ideas of slope or these rules aren't making sense, try and draw some pictures with them. I bet sometimes that helps make the rule a little bit stickier when we can see what we're actually finding, okay? We talked about the sum or difference rules, that if we have things that are all added together or subtracted together, that we could just do this rule we need for each part. We didn't need a special rule for it. But then at the end of class, and this is where I know that we're getting towards the end of a long lecture, and so I want to make sure we're really okay with this part, we learned about something called the product rule, okay? And part of what we talked about is sometimes you can simplify and you don't need a special product rule. But it was important for us to kind of practice the idea of product rule because we are going to get to situations where we are going to be forced to use that product rule, okay? And so as a reminder, product rule was just when you have two things multiplied together. When you want to find that derivative, you take the derivative of one, multiply it to the other, plus the derivative of the second one times the first one, okay? But maybe one thing I should add here is that it is not equal to the derivative of the first times the derivative of the second, okay? I think that's a really important point here, that multiplication is different from addition and subtraction. You can't just take a derivative here, take a derivative there, and then multiply them and then have your answer. Okay, so if you see a product, you should be using the product rule. Okay, so that brings us to the last rule that we're learning in 3.3. Okay, so the last rule that we're learning, and the part 2 that we're going to do today is all about practicing different ways that this shows up. Okay, so we're not learning any new rules in the second part of today. This will be it in terms of rules, but we're going to learn how to use these rules. Okay, all right, so whoops, sorry, quotient rule. Okay, so if we have y equals 3x squared plus 2x over x, find dy dx with 2 different methods. And so we're going to start here with the same way that we started with the product rule, which is, I'm going to see, can we rewrite this expression? Okay. And so before we try and rewrite that, I'm wondering if you can help me out with a couple numeric examples. So let's say that you have 1/7 plus 2/7. What do you get? You get 3/7. Okay. And maybe before we knew that it was 3/7, there is a split second where we thought 1 plus 2 over 7. And then we arrived at 3 over 7. Yeah. Okay. So what if I said this, 1 over 7 plus x over 7? What would that be equivalent to? One plus x over 7. Great. So 1 plus x in the numerator over 7. Okay, so like many things in math, we often practice this direction a lot, like common denominator, make it a fraction. Common denominator, make it one fraction. But what's important to know is that we can actually go the other way as well. And so what I mean by that is, if I had 1 plus x over 7, how could I write that as multiple fractions? Okay, 1 over 7 plus x over 7. Exactly. Okay, what if I got even fancier and I was like 2 minus x squared plus x over 9? How could I split that into different fractions? Okay. Anybody else come up with 3 fractions for this one? Okay. This does indeed break down into 3 fractions. So 2 over 9 minus x squared over 9 plus x over 9. Great. Okay, so now let's come back to this question. Okay, when I have this, y equals 3x squared plus 2x over x, how can I rewrite that as separate fractions? Third time's the charm, yes. All right, how do we rewrite this? Y equals 3x squared plus 2x over x. Three x squared over x plus 2x over x. Perfect. Same structure. Okay. Now, can we simplify even more? Sometimes we can, sometimes we can't, but it's always worth checking. Okay, and what does the 2x over x become? It becomes 2. Yeah, I buy that. That was actually something I noticed on exam 1 is some folks saw the 2x over x and they didn't go and simplify further. And when they tried to plug in 0 or whatever number I was asking you to plug in, it still caused a problem, okay? So if you have the same term in that numerator and denominator, you can go ahead and reduce that, that's okay. And if we think about how that rule applies to the first fraction, exactly, this squared and one of these goes away, so we end up with 3x plus 2. Okay. All right, so now that we've rewritten it, let's take derivatives. Okay, so y prime, yeah, no more fractions. Y prime, all right, let's see. I have two different terms here. I have my 3x and I have the 2, and they're separated by an addition. So that means that I can take the derivative of 3x, I can take the derivative of 2, and then add the 2 together. So what do we get when we take the derivative of 3x? I see 1 as a 3, okay? Now I'm going to write this out just in case. 3, I'm going to bring down the power of 1 and then x to the 1 minus 1, right? That's what we're really doing to get to that 3. Plus, what's the derivative of 2? Okay, yeah, I believe that that is going to be 0 because 2 is just a constant, okay? And so now that we've taken our derivatives, let's simplify or clean up our answer, and we'll get y prime equals 3. Okay. All right. So that is one way that you can do that. Now, if you can do a rewrite, I would highly encourage you to rewrite it. Okay. The next method that I'm going to show you requires us to do a little bit more work. Okay. It's not a bad way to handle the problem. And there are going to be questions where you have to use the second method. But if you can simplify and avoid this particular rule, I think that will actually make your life a little bit easier. Okay. So let's say we want to use this quotient rule, because when we're dividing, we're really finding a quotient. And so we're going to be able to use that quotient rule. So let's scroll down for a moment, see what this quotient rule says. Okay. So if two functions, f of x and g of x, are differentiable, then the quotient is differentiable. And f over g prime equals f prime g minus g prime f, or f g prime over g squared. Okay. So let's start with a setup. Last time I used the letters u and v. Yes, differentiable just means you can take the derivative of it. Exactly. Okay. But last time I used the letters u and v. And here they have f and g. Either way is fine. The f is like the u, it's just a letter that we're calling a function. The v is like the g, it's just the name for a different function, okay? So we're going to try this f and g notation for this particular example, just to show you we could use it that way as well. But if you prefer to use u and v as your letters, that is also fine. okay? So in my setup, that's going to be my first step. I'm going to set up. I'm going to have f equals, and then underneath it, I'm going to write f prime equals. Then I'm going to have g equals and g prime equals, okay? So if we look at the rule from below, what is our f in this particular problem, and what is our g? F is, let's go back to our original problem. Okay, let's go back to our original problem. So if we go back to the original, let's see, F, if I look at the formula, F is the part in the top. Okay, so let's go back to our original. That means this whole thing here, 3x squared plus 2x, that's our F. Okay, F is on the top. So then F is 3x squared plus 2x. Yeah. I think sometimes the hardest part is figuring out what the formula says and how to read it. Pick a good color. Okay. G. G in this formula is the bottom part. So let's go to our original. The bottom is X. Okay. So I'm going to zoom in now so we can take a look at this setup. Whoops, oh, not that far. F is the top, 3x squared plus 2x, and G is the bottom, which is X. We just got those as the bottom of our initial, the bottom of our initial question and the top of our initial question, okay? So maybe just to show us that it's not so scary now that we figured that one out, can we go down to example 14 for a moment? And I'm wondering if you could tell me, what is your F and what is your G? Okay, so let's look at number 14 for a second. What is our F and what is our G? Yeah, F is the numerator and G is the denominator. Spot on. Okay, so we've got F as x squared minus x minus 2 and G as x cubed plus 6. Okay. What's our F and our G for number 15? Good. Okay, so those are it for the examples that we have in this particular one. But when we're identifying these, we're really saying what's the top of the fraction, what's the bottom of the fraction, okay? So now let's go back to our original and see if we can make sense of the rest of it. So in order to plug things into the formula, we know our formula is y prime equals, let's see, let's make sure we copy this down correctly. F prime g minus f g prime over g squared. So f prime g minus, let me copy it correctly, f g prime over g squared. Okay, so in order to find this, to be able to substitute things into the formula, well, let's see what we have. We have f. So like, I know what to put right here. I want to put 3x squared plus 2 there. And I have g, which is what I'm going to put right here. Is there anywhere else that I'm going to be substituting that x? The bottom, perfect. So I'm going to put this down here as well. It's going to be x squared on the bottom, okay? Now, in order to substitute everything in, I need to find f prime and I need to find g prime. So we're going to go back to our setup and say, let's find our f prime, let's find our g prime. What's our f prime? Let's see how we're feeling about that product. I mean, the power rule. What's our f prime? 6x plus, ooh, okay. So we're gonna go with 6x because that is 3 times 2 is 6, x to the first power, so we don't need to write it. But what is the derivative of 2x? Yeah, it's 2. So we need to have 6x plus 2, okay? Now, if it were 3x squared plus 2, like no x there, what would the derivative of 2 be? Then it would be 0. Spot on. So good. So good. Okay, so this f prime is going to go right here in my equation. Okay. The only thing we need to find now is our g prime. Then we'll have everything we need to plug it into the formula. What do we have for g? Well, we have x. So our g prime gives us, da, 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 da. What's it give us? Yeah, 1. We're really thinking, what is the slope of x? And if you think about what x looks like, and you're drawing that line, it's going to be a rise over run of 1. Okay. So let's pick a lovely color for that one. Okay. So we've got f prime g minus fg prime over g squared. That is a mouthful. So let's plug in what we have and see what we get. 6x plus 2 times x minus 3x squared plus 2x times 1 all over x squared. So here's our 1. Here's our f. Here's our g, which we put in 2 different spots. And here is our f prime. Okay, so let's just make sure we see that this is the same as the formula that we had there. Okay. All right. Are there any questions before we go to simplify about where things came from, why these numbers or letters are the way they are?
I have a quick question.
Go for it.
If g was x squared instead of x, and we put it into the bottom where it's g squared, would it then be x? Would that simplify to x to the 4th?
It would.
Okay,
You know
cool.
what? Maybe to support you folks around that a little bit better, I'm going to put parentheses around that x. Okay, so whatever your bottom function is, you put that whole bottom function in there and you square that. Okay. By the way, folks, I know that for some of us, we know we learn really well by doing a bunch of different problems. But what I want to highlight about the question that was just asked is that there is power in doing one problem and saying, what if we change this to this? What if we change that to that? How does that change the outcome? Okay, because probably the question you see on the exam is not going to be one you've seen before, right? So the more you can prepare yourself for how to make decisions, the more you are empowering yourself to be able to solve a variety of questions. Okay, and I think that's one of the hardest things to sort of move towards in math, but I thought that question was excellent because it shows that idea that even though we have this one question, we're already thinking about how's it going to be for 14? How's it going to be for 15? Okay. All right. So as far as simplifying here, let's simplify. And we're going to get y prime equals 6x squared plus 2x minus 3x squared minus 2x over x squared. Now, the only reason I'm going to keep simplifying here is to show us that whatever answer we get on the right-hand side is going to match our answer on the left-hand side, okay? But in general, and I hope some of us are listening to this because I don't want us when we're doing homeworks and stuff to get too caught up on this stuff. But in general, when we're using quotient rule, I'm not expecting us to simplify a ton. Okay, I care more that you can plug things into the function in the right places and your derivatives are correct. And I care a little bit less about the simplifying for quotient rule. Okay, so there are some other resources out there that really want you to simplify a ton for quotient rule. That's not my general philosophy because usually we use quotient rule. It's not as important to simplify, okay? But if we did clean this up, we would notice that this 2x and this 2x go to 0. And we get 3x squared over x squared, which gives us 3. Okay. Now, let me ask you the same question I asked you on Monday. For this particular question, do we prefer the first method or the second method? Okay. Richard, it does not normally turn out that nice when it's simplifying. That's why I'm like, don't even worry about it. It's fine. Okay. Okay. So in this case, I think that by and large, the first method is more efficient. And what the first method also does is remind us of some important algebraic structures, like that we can split one fraction into more than one fraction, that we can simplify some things. And I think those are important to remember because they tend to come up a lot in math in general, okay? I think the quotient rule also is great because you're like, all right, this is the rule that works every single time I see something that's dividing, okay? But what I'm really trying to work us towards is this ability to make a decision. Which one requires less fake ink and which one might be like, what might you use when, okay? Yeah, well, I think we took this initial function and we dressed it up a lot and made it look more complicated than it needs to be. Yeah, exactly, right? That's what we showed right here is that it simplifies to a linear. And even just by, yes, so Aylin, save that question until we get to number 14, and then let's make that really explicit, okay? Perfect question. All right, so I already showed you the formula. Here's one.
Professor,
Yes.
sorry to interrupt. I just had two quick questions. The first being, does order matter? So could you do g prime of x, sorry, g prime of f in the front, and then have f prime g in the back?
If you did that, let's maybe use a numerical answer or question to answer that. So if I had 1 minus 3, what do I get?
-2.
Okay, and if I do 3 minus 1, what do I get?
2.
2. Are those equal?
No. So then what about the product rule? Does order matter in that one as well?
Ah, so product rule, what's the sign in between those?
It's addition.
It's addition. Okay, so 1 plus 3 gives you 4. What about 3 plus 1?
Gotcha. I see.
Okay. So I actually love that you asked that question. I know you said you had another one, but for
Okay.
folks who didn't catch what he's asking, if we see this minus sign here, okay, you can't just switch the order on both sides. You can't be like, oh, I'll just put this one in the front and that one in the back, because we don't end up with the same number if we try it with numbers. But he brings us back to a really good point that if we are adding things, then the order doesn't matter. Okay, so product rule, you might see it in a different order and that's okay, but quotient rule will always be this order.
Okay.
Okay.
Gotcha. Understood. Sorry. Okay. So the second question I had was, this has a, stipulation that both f of x and g of x have to be differentiable.
Mhm.
How do we know that?
So we're going to talk a little bit more about differentiability later on.
Okay.
But the short of it is, if you can find a derivative, so if you have an f and you know how to find the f prime, then it is differentiable.
Okay. I guess my question is, we're using a shortcut, but like if we use the fundamental theorem, isn't everything like have a derivative if you just like try for it? Like if we do,
And might it not have one?
right, because
Yeah.
right, that's what it's saying, right? Like
Yeah.
unless you're
Okay, so let's do this then.
okay. That was my second question. I'll just be listening. Thank you.
All right, let's go with the regular picture that we've been doing, something like this. If I asked us to find a slope here, I think we would all say that's like positive, right? If I asked us to find a slope here, what would we say that slope is? 0, okay. If I asked us to find a slope here, I think we'd say negative. Maybe when we get back to here, we're thinking it's 0 again. But if I drew like an infinite number of points on this curve, I could always find the slope there, okay? But let's think about cases that are a little bit less clear. Okay. What is the slope on this side? Positive. Okay. What is the slope on this side? Okay. What is the slope right here? Okay. I would say, let's think about our tangent lines. So if I were to draw a tangent line that touched this graph just at the top there, I could draw one like this, which is what you folks are saying, that the slope is 0. But I could also do this. Or I could do this. Or I could do this, or I could do this, or I haven't so many slopes. Because at that point, it doesn't just like change gradually. It changes like immediately from positive to negative. And so if we're looking at a smooth curve, like this one here, or like pretty much any kind of function that we've studied before, except for absolute value, because they're all smooth, we say that they're differentiable. But our absolute value graph is actually a great example of a case where there's this one point that is problematic because it changes so suddenly, so drastically, that we're not able to find the slope at that point. And so we would say that the second graph is not differentiable. Does that clarify what you were asking about, Moon?
Absolutely. Thank you. Okay.
Cool.
I guess just the follow up then, is there like a practical way to know, or you just see absolute value and you're like, okay, that's not differentiable, and then you just like move on?
So we'll talk about some common pictures to look for, but I think it tends to be that when we're looking at things, it's important, or when we're looking at equations, it's important to have a general idea of what those pictures look like.
I see.
Yeah.
Okay. Thank you.
Welcome. Thanks for asking that question. Okay, so this sort of next part is that the quotient rule is kind of like a gross looking rule. Like it's got a fraction in it, there's subtraction, we're squaring some things. And so I've heard these other variations over the years. They might be more helpful to make the quotient rule sticky in your brain about what goes where. Some folks like to say that if you have a function on the top, that it is higher than the one that is below, which is lower. Okay. And so if we were trying to use the quotient rule here, we end up with low d high. So d is like a derivative. Okay. So the lower function, which is our g, times d high, the derivative of the top function, minus f is high, so high. And how do I write g prime using these letters that I have here? Yeah, high d low. Okay, so low d high minus high d low already sounds much more friendly than f prime g minus f g prime. And then on the bottom, another way of saying squared is that you have something times itself. So throw out for, or shout out for anyone there who is has a low. Okay. If you have a low, you know what I'm talking about. All right. So low d high minus high d low over low. Okay. So that's like sort of a more fun way of remembering the rule if you like. And then what else have I heard? Some people just prefer the letters U and V, so kind of boring, but they like the letters U and V better. So you might just see someone who has this. And so you might see the rule written as V du minus U dV over V squared. They're probably super tan. I'm sure with the creative minds in this group that you could find one that is much more clever than what we have here. So have some fun with it. See if you can find some ways to make things sticky for yourselves, okay? But these are just a couple alternatives. All right, let's move on to situations that sort of address Aylin's question about how do we know when we have to use quotient rule and how can we get away without using it, okay? So for better or for worse, the next two examples, we have to use quotient rule, okay? And so to sort of think about what might be the giveaway, like how do we know, is if I were to try and split this fraction here, I would end up with something like this: x squared over x cubed plus 6 plus x over x cubed plus 6 minus 2 over x cubed plus 6. So I can split this fraction into 3 fractions like I did with example 13. Do any of these 3 fractions simplify even more? Yeah, not really, right? And so what I've done is I can split them into fractions, but now I've made it worse because I have to use quotient rule here, and then I have to use quotient rule here, and then I have to use quotient rule here, and then I have to combine all my different parts. But that sounds like not fun. So sort of to answer that question from earlier, if you are looking at that denominator, the denominator is our tell sign, okay? So yes, if you can factor the initial fraction, you're good to go. But more significantly, if the denominator just has one term, I would try and simplify and not use the quotient rule. That is, if you see something where it's 2 terms, use the quotient rule. Okay. Aylin, does that answer your question from earlier? Okay, cool. All right, so to that end, because yes, exactly. If you could somehow make an x cubed plus 6 happen in the top, good to go, cancel some stuff out, move along. But we can't really here, so we're gonna just use the quotient rule, okay? All right, so we've got our F and our G, okay? And if you like, maybe we change those. You don't have to U and V, just so we can sort of see that different notations mean the same thing. U prime is the same as du, so however you choose to write it is fine. And V prime is the same as dV. Okay, so take a moment, figure out your derivative for the top, figure out your derivative for the bottom. And when you find those, throw those into the chat. All right, 2x. Ooh, I'm going to ask you to modify one thing there, Thea, and I'm not sure if it's just a typo or not. Or if anyone else can spot what is the one thing we need to change about Thea's response. Yes, exactly. Okay, so we have 2x, but it's a minus sign in between x squared and x, so minus 1. Okay. What happened to that 2? How come there were 3 terms and now there's only 2 terms? Like, what happened to that 2? Yeah, that became 0. And so if it's helpful to you at this stage, you're totally welcome to sort of think about how each one corresponds to another term and write out that 0. There's nothing wrong with that, okay? But it's also okay just to write 2x minus 1. All right. Oh, that's the other. Yep. Okay. So, oh, wait, I copied it wrong. Woo! Happy Wednesday. Plus and plus and plus. You were so right. I'm 100% wrong. I know. And I have a tablet, so it's so much easier to get rid of my mistake. Okay. All right. Let's make sure we copied down V correctly. X cubed plus 6. Okay. Right? Erasable pens. Oh no, please. There are definitely going to be mistakes. So it's definitely helpful when folks point that out. All right. What do we get for dv or v prime here? 3x squared. Love it. And again, totally okay to add a plus 0 here if you're like, what happened to that 6? Okay. And then once you've convinced yourself that that derivative of 6 is a 0, then you can just write it as 3x squared. Okay. All right. We good on the setup? I bet some of you have already worked ahead, but if there are any questions about the setup, let's address them now. All right. So now we sub into our formula. Now, because we've used u's and v's, I'm going to say that y prime equals v du minus u dv over v squared. And I'm going to be really careful to make sure that I substitute everything in correctly. So x cubed plus 6 times 2x plus 1 minus x squared plus x minus 2 times 3x squared all over x cubed plus 6 squared. Okay. So let's take a moment, make sure that that setup gives us the substitution, that we put everything in the right place. Okay, so we're going to simplify now. We're going to simplify the numerator only, okay? I'm going to keep that denominator as x cubed plus 6 squared. And I'm going to ask that you do the same for your assignments, okay? Being able to FOIL is something that we sort of expect that we know how to do at this point. So it's almost like because we don't really need to FOIL, we're just going to be a little bit lazy and not. Okay. I do think it's important to practice simplifying the numerator just to make sure we're good with like our exponent rules and combining like terms and things like that. Okay. And so when we take a look at that numerator, I believe, let's see, we get 2x cubed, 2x to the 4th plus x cubed plus 12x plus 6. And then minus 3x to the 4th minus 3x cubed plus 6x squared. And let's combine our like terms. We get negative x to the 4th minus 2x cubed plus 6x squared plus 12x plus 6 all over the denominator squared. Oh, okay. So anybody else notice that we had an x cubed plus 6, and on the bottom we have an x cubed plus 6? Okay. So this is actually a really great moment to talk about some simplification rules when it comes to like reducing fractions. That's really important to remember. Okay. I've seen people who look at this question. Actually, let's back up a moment. I've seen people who look at this and say, awesome, let me get rid of those x's and I get 5. Okay. Now, the funny thing is if I ask that same person, what is this? They will always tell me 7 over 2. And they know that that is not equal to 5. And so that idea of canceling the x's doesn't quite work. But I think the reason why it doesn't work is important. So when we're reducing because things are factors on the top, meaning everything is multiplied by each other. So what I mean by that is if I had x times 5 over x. Okay, so everything is multiplied on the top, everything is multiplied on the bottom, then I can reduce and I get 5. And if I plugged in a number, 2 times 5 over 2, I would get 10 over 2, or I would get 5. Okay. So the thing we need to be really careful about, especially in our language as we think about factoring, is that if we have terms that are combined by addition or subtraction, then we have to be really careful about reducing, okay? Now, to your point, Richard, if you had found that there was an x cubed plus 6 times a bunch of other stuff on the top, and then you had x cubed plus 6 squared here, you could reduce one of those, okay? But we don't have x cubed plus 6 as a factor. It's just in a string of addition at the top. Does that make sense? Always a good place to check yourself and think about whether we're canceling correctly. I'm actually really glad you noticed that because I did not notice that when I was working out the problem myself. Okay, but what we have here is our derivative, okay? And now keep in mind all this work that we did, this is a shortcut. This is a shortcut for that formal definition where we have to have like the x plus h and the x and then subtract them and then find that limit as h approaches 0. Okay, so this is actually, even though it is substantial in the amount of work we've shown, is a shortcut for that formal definition. All right. For the sake of time, I'd like us to set up number 15 in the sense that let's find our D high and our D low, okay? And once we find them, I will work out the answer. I'll post a solution here when I post the notes. But I'd also like you to kind of practice a little bit more and give you a chance to sort of try it on your own and then be able to check with an answer key, okay? So in this case, we've identified our high and our low. Let's start over here. What is our D low? Two x, beautiful. 2x minus 0, if you like to think about it that way, which gives you 2x, okay? Now, when I think about finding the derivative of the high function for square root of x, it might be more helpful to write high as 4x to the 1/2. Then when we find our derivative, we've got 4 times 1/2 x to the 1/2 minus 1. And that's going to give me 2x to the negative 1/2. Okay. Or we could write that as 2 over root x. So we can start to see that like quotient rule doesn't mean just quotient rule. It means we're using power rule to help us out as well. Okay. And that is sort of going to be the flow of a lot of these questions. It's never just going to be one rule. It's going to be like product rule, quotient rule, power rule. We're using them kind of all together, and we need to be able to make those decisions. Okay. So I'll leave you here to plug it into the formula, simplify numerator only, and I will post the rest of this when I post the notes for today. Okay. All right. Any questions here before we pause for a break?